In geotechnical engineering, analyzing an earth dam model inside a hydraulic drainage and seepage tank allows you to visualize how water moves through an embankment. This experiment lets you plot the phreatic line, the top water level line, and map out a flow net, a grid of flow lines and equipotential lines to calculate seepage discharge and assess piping risks. Equipment and materials. Drainage and seepage tank. A narrow, transparent sided tank, typically glass or acrylic, fitted with adjustable overflow pipes to control upstream and downstream water levels. Piezometer bank. A row of vertical glass manometer tubes connected to tapping points along the back wall of the tank to measure pore water pressure. Hydraulic head. Soil sample. Well-graded, clean silica sand, e.g., Leyden Buzzard sand, to form the dam body. Dye injection system. A reservoir of dense coloring agent, such as potassium permanganate or fluorescein dye, equipped with fine-tipped needles or glass tubes to trace streamlines. Template tools. A trapezoidal template to shape the dam, a small tamper, and a grid scale overlay on the glass. Step-by-step experimental procedure. 1. Constructing the earth dam model. Dry packing. Thoroughly clean and dry the inside faces of the glass tank. Place the sand into the tank in uniform layers, 50 text to 75 text thick. Compaction. Lightly and evenly tamp each layer to avoid creating internal voids or artificial stratification, which would skew the flow lines. Shaping the profile. Use a rigid trapezoidal template to trim the sand into a standardized earth dam profile, creating fixed upstream and downstream slope angles. A common configuration includes an internal horizontal sand filter or toe drain at the downstream base to prevent sloughing. 2. Saturating the system, slow filling. Priming from downstream. To prevent trapped air pockets from blocking the soil pores, slowly introduce water into the downstream pool first. Equilibrating. Once the base is saturated, slowly switch the inflow to the upstream side. Raise the water levels gradually. Rapid filling can generate high internal seepage forces that cause the unconfined sand slopes to collapse before steady-state flow is reached. Setting the heads. Adjust the upstream overflow pipe to a fixed high level H_text upstream, and the downstream pipe to a low or zero tailwater level H_text downstream. 3. Establishing steady-state flow. Keep the continuous water supply running until the water spilling over the overflow pipes remains perfectly constant. Monitor the wet boundary cutting through the dry sand of the dam profile. The phreatic line, the topmost water level line within the soil, is established when this boundary stops moving. Below this line, the soil is completely saturated. Above it, it is unsaturated. 4. Injecting the dye to trace flow lines. Position the dye injection needles just beneath the surface of the saturated upstream slope, spacing them evenly apart. Adjust the dye reservoir height until the dye fluid pressure matches the local hydraulic head. If the dye bleeds out in wide clouds, the reservoir is too high. If water backflows into the needle, it is too low. Watch as steady, distinct colored lines, flow lines, begin to travel through the sand matrix from the upstream face toward the downstream toe. Data collection and mapping the flow net. Step 1. Mapping the water level and flow lines. Using a washable marker or a grid overlay directly on the transparent front glass of the tank, trace the following. The boundary of the upstream pool. The exact path of the visible colored dye lines, streamlines. The top edge of the saturated zone, phreatic line, which acts as the uppermost flow line where pore water pressure, U equals atmospheric pressure, U equals O. Step 2. Measuring the hydraulic head. Look at the vertical piezometer tubes mounted on the side of the apparatus. Record the static water height in each tube relative to the base datum. Each reading represents the total hydraulic head H at that specific tapping point location within the dam. Step 3. Drawing the equipotential lines, graphical construction. Transfer your traced flow lines onto a sheet of paper to construct a formal, orthogonal flow net using standard geotechnical design rules. 90-degree rule. Draw a series of smooth curves, equipotential lines, that intersect every single flow line, including the upstream boundary, the phreatic line, and the impermeable base boundary, at perfect 90° right angles. Curvilinear squares. Adjust the spacing of your equipotential lines so that the grid shapes form curvilinear squares. You can verify this by checking if a circle can be drawn inside each grid space so that it is tangent to all four bounding curves. In geotechnical and civil engineering, earth dams and levees are among the most critical pieces of infrastructure because they are constructed using the most unpredictable material available, natural soil. Unlike steel or concrete structures, which are manufactured to strict specifications, an earth dam must safely contain massive forces using local geology. Because a mathematical equation can never fully capture the complex, real-world behavior of water moving through soil, physical laboratory experiments using seepage tanks and hydraulic apparatuses are foundational. Here is why dam experimentation is absolutely critical to geotechnical engineering. In conclusion, dam experimentation acts as the bridge between abstract theory and real-world safety. It proves to future designers that water flow through Earth structures obeys the laws of physics, gives them an intuitive understanding of how soils fail, and ensures that real-world infrastructure is built with an adequate factor of safety against the devastating power of water.